Okay, chapter 4. So we've done linears, quadratics, and so we're going to take it up a notch. Chapter 4 is a really big section. I'm actually going to break it down into part 1, part 2 when we come to the exams, because there's just a whole lot of information in chapter 4. So chapter 4 is higher degree polynomials. All right, higher than quadratics means we're going to get third degree, fourth degree polynomials. We start there and then we get into rational functions, which is a division of polynomials. Alright, so first, nonlinear functions and their graphs. So we're going to specifically look at polynomials. What a polynomial is, its behavior graphically, and how we can tell its behavior by looking at its formula. Determine the extrema. Max and mins are always important to determine because applications tend to involve max and mins. And symmetry. A lot of our polynomial graphs will have symmetry. Alright, and there are two types of symmetry we're going to look at. So a polynomial is what we're dealing with in this beginning of this chapter. So polynomial is a function. So all polynomials are functions. The highest powered expression in the function is its degree. Alright, so you'll notice here this is the degree n. It's the highest power. So all of these are lower powers, right? N minus 1. So if it was a fifth degree, that would be 5. The next one would be 4, and so on, moving down. That highest degree is paired with the leading coefficient. A leading coefficient is actually going to be very important. That leading coefficient is going to tell us a lot of information about our graph. Polynomials, and actually linear functions and quadratics are polynomials. They're just the special types of polynomials we tend to look at because their behavior is one that we typically can deal with, and they're the lower degree polynomials. Alright, so some examples of, again, some formula and their degrees, just so that we can understand, because it's important. The degree tells me about my polynomial. Now, what's nice about polynomial is the domains of these polynomials are always all real numbers, so domains are everything. Polynomial functions are smooth and continuous, meaning I can draw the entire graph without lifting my pencil up. Right? There are no holes, breaks, gaps, or asymptotes. And so here are some examples of polynomials. So the first two are lines, right? F of x is 10. That's a horizontal line. Has a degree 0, right? Leading coefficient of 10. The second one, g of x, is a linear function, degree 1, right? Linear functions of degree 1 or 0. All right, its leading term is the 2, right? It's the term paired with the x. The second one's a quadratic, right? Degree 2, all quadratics are degree 2 polynomials. Its leading term is that 3. And then the last one is a high degree polynomial, which is what we're going to get into in this chapter, high degree polynomials. Its highest degree is 6. Its leading term is that negative 1/2 out front. And again, we're going to use the leading coefficient, and the degree will tell us a lot of information about my polynomial. Alright, so determine if these functions are polynomials. Yes or no, they're polynomials. If they are polynomials, what's the degree? And those that are not polynomials, you should understand why they're not polynomials. All right, I'm also going to give the leading term. All right, so the first one, yes, it's a polynomial. Say it's going to be a polynomial of degree 1. Its leading term is negative 1/2, right? The negative 1/2 of the x. P of x, though, is not a polynomial. The x, if I were actually to rewrite this, I'd move the x up and make x to the negative 1. Polynomials, the degree has to be, and again, I didn't point this out, but I'm going to point it out now, a non-negative integer, meaning a positive, non-negative, whole number value. Integer means a whole number value. So 0, 1, 2, 3, 4. No negatives and no fractions. And so this one fails because this x actually has a negative exponent. If I rewrote that, it would really be 3 minus 1/2 x to the negative 1. Well, that is a negative number, so it's not a polynomial. It's a rational function, not a polynomial. Alright, the next one, g of x. G of x is a polynomial. It's just a polynomial in factored form. Now, the hard part about factored form is to figure out the leading coefficient and the degree degree of it, but what you do is you basically multiply the highest x value, the highest variable part in each group. So x, x squared, and x, if I multiply those three terms together, my leading term would be x times x squared times another x would be x to the fourth. And it would be x to the fourth because there's no numbers. It's a 1 in front of all of those, and so 1x to the fourth would be my leading term. And so yes, it's a polynomial. It's just in factored form of degree 4. The leading term, or the leading coefficient, is 1 in that case. The next one is not, and it fails the power rule. The exponent on this, or the power on this, is a fraction. There are no fractional degrees, and so not a polynomial. It's a power function. Alright, so not. The last one is, this is a polynomial, the square root's only on the 5. Alright, so degree 3, degree 6, this is the highest degree, and so yes, it's a polynomial. And its degree is a 6. Its leading term is 7. Alright, 7, this is the leading term. Alright, so polynomials are when you have numbers in x terms multiplied by number multiplied by an x term. The x term has a power, and that power has to be a non-fraction and a positive number. So it means non-negative, positive, integer, not a fraction. And the leading coefficient is just the number out front. And again, the biggest degree, the biggest number on my power is my degree. Alright, so polynomials is what we're going to dive into here in this section. So the next part is where we want to find extrema, right? That's very important. A lot of applications want to know max and mins, and so that's the next thing we're going to look at.